In the previous section, we focused on limits, and now we're going to use limits to define something called continuity. And it's really important that we understand continuity because a lot of the rules and the theorems that we're going to talk about rely on the function being a continuous function, or at least continuous over an interval. So let's first talk about the general idea of continuity, and then we'll get into that rigorous definition. So when you think about continuity, what I want you to focus on is when you look at the graph, are there going to be any holes or breaks or asymptotes in the graph? At those funky points where you have something weird going on, those are going to be your points of discontinuity. Another way you could look at it is if you can draw the whole graph without picking up your pencil from arrow to arrow, from one end to the other, then that would be continuous, because you don't have to lift up your pencil because there's a hole in the graph or if there's an asymptote or a jump. So intuitively, that's what you're looking for to see if something is continuous. And this is that question that keeps popping up about the fundraiser dance. And when we talked about it before, that breaking point at 150 was where the profit function broke in pieces, because the profit function is going to change depending on whether or not the number of people that attend the event are below or above 150. Once it goes over 150, we had to adjust that profit function, because then we would have to get a security guard involved and pay him for his services. Looking at the graph of this piecewise function, we have some kind of quadratic here. We have some kind of quadratic here. Here and here, along the y-axis, there is not a value for the function at this point 0, 2 or x 0, 0, but rather the value of the function lies right here at 0, 3, because this is closed and these are open. So when we think about continuity intuitively, we want to make sure that there are no breaks or jumps in the graph. So when we look at this to figure out what we need to do to make this continuous, so this is going to help us determine the official criteria for a function to be continuous. When we look at each piece, first of all, we see this big gap right here. So one thing we want to do is make sure that this circle here comes down and overlaps with this. So right now, the function, if I looked at the limit coming from the left, the limit would be 0. I'm getting closer and closer and closer to 0. If I look at the limit coming from the right, the value of the function is getting closer and closer to 2. So in order to close that gap, I need to make sure that the limit coming from the left is the same as the limit coming from the right. So to close that gap, we would just move that piece of the function down, and now we only have one concern here, which is this hole. However, let's double check. If I come from the left, my limit is 0. If I come from the right, my limit is 0. So one of the important criteria that you need to check for continuity, if there's a point that you're concerned about and you want to check, you just need to make sure that the limit coming from the right is the same as the limit coming from the left. Now this function still is not continuous, because I have this right here is different than the actual value of the function. At this point here, we have a removable discontinuity. So in order to fix that, to make sure instead of having this point here, we want to plug that hole so that we don't have a hole there and it's continuous. So what we would do is take out that 0.03 and put that right here, plug the hole. So now if I got rid of that 0.03 and plug that hole, now we have a point there. There's not a hole that we would have to skip over. There's no jump because the limit from the left is the same as the limit from the right, and the value of the function exists there. We want to make sure that the value of the function is here and not up here. Now that we have a conceptual understanding about continuity, and we looked at a graph that was discontinuous and we moved pieces around to show how we could make it continuous, now we have an understanding, an intuitive understanding of what the rules are. And there's 3 of them. So here's our official definition for being continuous. So here's our official definition for being continuous at a certain point on a function. So we have a function f here, and we want to check to see if it's continuous on a specific point. We're going to name it A. So the following conditions have to be satisfied if we want the function to be continuous at that point A. So first of all, we want to make sure that if I plug in A into the function, we are going to get out a value for y. We need to make sure that the value of the function exists at that point A. Then we talked about when we have a jump in the graph. If we have a jump in the graph, then the two-sided limit is not going to exist, because when we have a jump, that means the limit from one side is going to be different from the limit coming in at the other side. So the two one-sided limits exist, but not the two-sided where they come in and meet together at that same point. Then the last thing we talked about is plugging that hole. So we could have a function that has a point defined at A, but the limit could be different than that value of the function. So these are the 3 rules that we need to make sure happen to be continuous at a specific point. All right, so here's some examples of how you need to be able to identify where we have a concern on the graph at a specific point, and we want to check to see if it's continuous or discontinuous using our rules. In these 3 examples here, we're going to look to see if it's discontinuous, what rule did it break, and if it's continuous, then we're good to go. So looking at graph A, the value of the function is not defined at that value 2. So right away, it does not meet that first rule, where the value of the function has to exist. Now let's look at example B. For the graph in example B, the value of the function exists at 2, but it's not the same as the limit coming from either side towards that point, x equals 2. So the limit from the left and the right are both approaching 3, but the value of the function is 1. So it is not continuous, and it's breaking the 3rd rule. The limit has to be equal to the value of the function. Okay, now looking at part C, when the hole was plugged, so now the value of the function is the same as both of the limits coming in from the left and the right. So in this example here in graph C, this is continuous at x equals 2. So in the example we just did, we were looking at graphs of the functions in order to determine the points of discontinuity. Now we're going to look at the piecewise functions with the equation rather than the graph. How do we find those points of discontinuity when we're looking at the equation? So first of all, sometimes we get hung up on where the pieces meet up that we forget to look at the equation itself, like that formula for that piece. So looking at this right here, let me get my laser. So looking at this piece right here, that's a linear function. We know it's just going to be a slant line, mx plus b, and we also know that there are no holes or anything funky going on with lines. It's just a straight line. Same thing here. This is a linear function. All of these looks like they're linear functions. So there's not anything concerning about these. If one of these equations for one of the parts was something like 1 over x, Then, in addition to looking for where the pieces meet up, we would also want to look at that piece and see if we're going to run into a problem with 0 in the denominator. That's the first thing. Then, once we get through looking at the equations of each piece, then we want to look at where the pieces meet up. Because if the pieces don't meet up in the right way, then there's going to be a gap or a hole or something like that, and then we're going to have a discontinuity. So when we're looking at piecewise functions, it's really important to look at where the pieces should be lining up. We want to go through those 3 rules to check to see if it's continuous. And the first rule was we want to look to see if the value of the function exists at that point that we're concerned about. In this piecewise function, we're looking at specifically x is equal to 4, because you can see in the domain of each piece, that's where the break is going to happen for each piece. So if I look at the first part where it says x is less than or equal to 4, this right here, that is going to be the piece of the graph that would contain the value of the function at x equals 4 if it exists, because we're saying on this interval we're including 4. So to check to see if the value of the function exists at x equals 4, I'm going to plug in the point here, and I have 4 times a half, which is 2, and then 2 minus 3, that's negative 1. So we know that the value of the function exists. The value of the function at 4 is equal to negative 1. Now, the next thing we need to look to see if the two-sided limit exists. So we have to check to see if the limit from the right and the left are meeting up and approaching the same point. We want to check what happens to the value of the function as x gets closer to 4 on either side. So for this side here on the first piece, that is where x is less than or equal to 4. So that means we're looking at the x's that are smaller than 4. So this is going to be the case where we're coming in from the left. So coming in from the left, we know that when the value of the function exists there, it's going to be negative 1. We just checked that. So coming from the left, the limit is negative 1. Now, this piece here are all the values greater than 4. So when we look at that piece, we're going to be coming in from the right. So as I come in from the right, as I get closer and closer to 4, the value of the function gets closer and closer to negative 1. Because as I put points in here that it's getting closer and closer and closer to 4, we're getting closer and closer to negative 1. So we can definitely say that this function, part A, is continuous at x equals 4 because it met the 3 qualifications. So the value of the function exists at 4. The two-sided limits exist, coming in from both directions, it's the same limit. And then also the value of the function is equivalent to the limit. They're both negative 1, so we don't have that case of a removable discontinuity. All right, so let's look at part B. If we check the value of the function at 4, this first piece right here is what contains the value of the function when x is equal to 4 if it exists. When I plug in 4 here, I get negative a half times 4, which is negative 2. When I add that to the 4, I get 2. So we know that the value of the function exists at x equals 4. Its value is 2. So now let's look at the two-sided limit. This piece right here is going to be the values that are less than 4. So we're coming in from the left on this piece. As we get closer and closer to 4, the value of the function there is going to approach 2. Now, if we look at the limit from the right, that's where the values of x are greater than 4. So we're getting closer to 4 coming from the right. That's going to be really close to 12, and 12 minus 9 is 3. So the limit coming from the left is 2. The limit coming from the right is 3. So there's going to be a jump in the graph. The limit from the right and the left are not equivalent. So that's breaking rule number 2, where the two-sided limit doesn't exist. Let's look at part C here. I can see by looking at this right away that this breaks rule number 1. the value of the function at x equals 4 here does not exist. It's either less than 4 or greater than 4, but not equal to 4. So this breaks rule number 1. So in this example, it says some people, when placed in extremely stressful situations, they exhibit explosive bursts of anger. And such behavior might be described by the function pictured below. And it says the horizontal axis records the amount of stress. So there's some kind of scale that they use to indicate a stress level, and that's going to be on this horizontal axis. And then it says the amount of anger is going to be on the vertical axis. So they have some kind of stress scale that they can measure at different levels. What else here? It says make a statement about the continuity of the function at x equals, oh, that's s equals c, and give a possible interpretation to the point s equals c. So when we look at this, we can definitely see that the function is discontinuous because at c, we have that jump in the graph. And that tells us that the limit from the right and the left are not equivalent. So we definitely have a discontinuity because of rule number 2. Now, to interpret what this means, remember the horizontal axis here represents the stress level, and then this axis here represents the anger level. So as we come across this way, our stress level is getting greater because think about it moving horizontally, that's our stress level. So as our stress level gets bigger, this piece right here is increasing, and then it jumps. So this person has kind of like a break. It's not just a break in the graph, it's a break in his stress level. He's gonna lose his cool. So that's here. And then when he reaches his limit, when we keep going this way, notice that the function starts to decrease right here. So as we move right to left, we notice this was his anger level, and notice that this is flattened out right here. And at this point right here, he starts to level off with his anger, and then his anger starts to decrease. So I would interpret this as this piece here, he gets angrier and angrier, and then he meets his breaking point, and then up here he starts to cool off, his anger flattens out, and then it decreases, and he starts to feel a little bit better. So a couple more rules, and these are fairly easy. When we think about polynomials, we know that we're talking about linear functions, we're talking about quadratics, cubics, quartics. Those functions that are polynomials do not have anything weird going on, like no holes in the graph, no asymptotes, no jumps, nothing like that. So we can say for certain that every single polynomial function is continuous on every open interval. No matter what interval you pick, it's going to be continuous because it's continuous everywhere. For the second rule, when we think about rational functions, like if we think about the function 1 over x plus 1, that is going to be continuous everywhere except for when we get 0 in the denominator. So every rational function is continuous on every open interval and every closed interval except for intervals that include the values of x that creates 0 in the denominator. That's when we're going to get something funky. So let's look at a couple of examples. So looking at example 5, let's see. Example A, that is a polynomial. That's a cubic. We have x to the third plus 3x minus 1. So right away, we know automatically that's going to be a continuous function. No matter where I pick my interval, or no matter what point I'm looking at, that's going to be continuous. This function here on part B, that is a rational function. So that should be continuous everywhere except on points that create 0 in the denominator. So the way that you can figure out what creates 0 in the denominator is you're just looking to see what value of x makes that x squared minus 7x plus 12 in the denominator equal to 0. So you just want to take whatever's in the denominator, set it equal to 0, and you want to solve. Because that's a quadratic, we have different ways that we can solve it. We can factor or use a quadratic formula or complete the square. So whatever method you would choose to use, you're going to find for this quadratic function, there's going to be 0 in the denominator when you get x equals to 3 or x equals to 4. So that function in part B is going to be continuous on all points except for 3 and 4. If you write it in interval notation, it's going to look like this. We never use bracket with infinities. We always want to use parentheses. So everything from minus infinity up to 3 is going to be continuous, but not 3. That's where it's going to create a 0 in the denominator. So that's why we put a parentheses here to say we're not including 3, just everything up to 3. Then we're going to put a union symbol here. That's telling the reader that we're going to join several different intervals together to create the domain. So the next piece, if you think about going left to right on the graph, we have a discontinuity at 3, and then we keep going right, and then when we hit 4, we have another discontinuity because that's where it creates 0 in the denominator. So then we have to skip over 4. So not including 3, everything between 3 and 4, and then skip over 4. So that's why we have the parentheses with 4. Then we join that last interval. We want to go from 4 up to infinity. So a way to look at it is we are saying that this function is continuous everywhere except for 3 and 4. So we're going from minus infinity all the way up to positive infinity, but we're skipping over those points 3 and 4. So we have to make those breaks in the domain. So now that we've got a good idea of what continuity is, we understand how to find it from looking at a graph, from looking at an equation of a function. We understand the rules that, if broken, will define the function as not continuous. So now let's take the idea of continuity. We're going to apply it in this first example here up at the top. We have two graphs. We're going to think about this in the context of a hotel business. So I actually want to look at graph B first, and then we'll go back and look at A. When you look at this graph right here, I want you to think about a hotel manager that wants to do some research to determine the occupancy at certain weeks throughout the year. He wants to determine when he has his high points and low points so that he can make some decisions. He wants to determine how much food should I order for the hotel restaurant during this time frame, or how much soap and other supplies that I need for my guests, during this time frame. So he needs to be able to make an estimate about the hotel occupancy. So over a period of a certain time, he collects data. He goes to one day and he says, okay, I have this many people in the hotel, and he starts to collect data. Then he plots it on a grid. So on the bottom here, we have weeks. On the vertical axis, we have occupancy. This is called a discrete graph because the values that are on here are countable. I can sit here, even if there was a lot of them, if I can sit there and count how many points there are, no matter how many, no matter how big it is, if I can count it, it's called countable. Now, switching over to graph A now. If the hotel manager wants to then use his data to make a guess, an educated guess, on what happens over a certain time frame, and he doesn't have collected data for that time frame, then what he can do is he can imagine that he's creating a curve like this that puts those points together. So he's pretty much filling the gaps between all the data values. And when he does that, he gets a continuous function. So although the data that he collected is discrete, he can use the discrete data to create a continuous function. And the benefit for that now is if, let's say, this point right here represented, let's say, week 1 in his study, and let's say this value right here represented week 5. So if he only has data that he collected from week 1 to week 5, and he wants to estimate what the occupancy is between week 1 and week 5, let's say week 3. So then when he looks at this graph instead, where he connected the dots to get an idea of what happens in between, he has a continuous function, and now he knows he has a value of the function at week 3. There's no gap there. So he can use that function that he created to make an estimate of what might happen as far as occupancy during that week 3. So when we fill the gaps like that, and we go from discrete to continuous, we're making the graph more usable. If I use only these points, then what happens in between the points isn't really going to help me. But if I make it a smooth curve, then I can use that to estimate what happens between the points. So we're making it more usable. And when we do that in business, it's called idealized. So it's the ideal graph. So let's look at this graph down here, graph 8. This graph measures velocity at a certain number of seconds. And so you can have 1.5 seconds and be going at 54.7, let's say, miles per hour. The velocity is going to increase and decrease in a way that we have no holes and breaks in the graph. The driver isn't going to drive for, say, the first 8 seconds and then automatically stop, make a hole in the graph so that there's no value for the velocity there, and pick up where he left off at 8.1. That's just not going to happen. So velocity is really, it's going to be continuous. So this graph, you could say, is already idealized because the graph, without making any adjustments to it, is very usable. Here is our last example for this lesson. We're going to look at another comparison between 2 graphs, one with real data and then one that has been smoothed out and made continuous so that it's easy to use to make estimations. So we call that usable or idealized. So this graph here is of someone keeping track of their weight because they're trying to lose weight. And down here on the x-axis, we have the number of weeks. And then on the vertical axis, we have the amount that the person weighed at that week. So as you can see, it's very smooth, it's continuous, but this doesn't represent real life. It's been smoothed out and made more simple to follow a pattern so that it's easy to use to make estimations. If we were to look at real data in real life, you're not going to see that smooth curve. You are going to see a bunch of dots where she collected the data, which was her weight, and then at that week, she marks it on the graph. If we look at the real data or the real graph, so at different weeks, she collected her weight and graphed it. And as you can see, this one is more bumpy and it's more realistic, not only because you can see the data values that were actually collected. You can see where she gained a little bit back and she had a bump and then she, came back down and lost some more weight. In real life, it's not going to be perfectly smooth. So things that you should be able to answer once you practice and you feel more comfortable with it. These are some general conceptual questions. When you start feeling comfortable with continuity, go back and try to answer them.